Traian Iliescu is a professor at the Department of Mathematics at Virginia Tech in the United States. He won the SIAM Student Paper Prize in 1999 and received his PhD in 2000 from the University of Pittsburgh. He was in the years 2000-2001 the Wilkinson Fellow at Argonne National Laboratory and joined Virginia Tech in 2002. His research focused on numerical simulation and analysis of turbulent engineering and geophysical flows with a special emphasis on reduced order modeling. And his talk, the title is Large Eddy Simulations by Reduced Order Modeling, sorry. Thank you, Traian.
Thank you, Tomas. Thank you. Well, first of all, let me thank Tomas again for putting together this seminar, and of course our fearless leader Angelo Iolo for putting together this team. It's a pleasure to give a talk in here. So today I will talk about large eddy simulation, reduced order models. This is the outline of my talk. And really, so what I want to do is to give you an overview of what we've been doing in our group for the past decade or so. And really, this can be put in very simple terms. We're trying to put together two fields. So two distinct fields. There's large eddy simulation. I think quite a few of us have background in this, and reduced order models. And this is, again, quite a few of us have, a lot of background in this, okay? My aim is, as Samuele pointed out in his talk, is to target turbulent flows, all right? And here's my sales pitch. So I want to emphasize that what I really would like to convey is the principles that are used in order to put together these fields. So first of all, I want to answer why we should do that. So that's my sales pitch. And then how we plan to do this, to connect these two fields. Now, the models, the actual computational models are not the focus, although that's what I'm selling, right? So I will present models, but once again, the principles, in my opinion, are more important. Okay, so this is the outline of my talk. I will start with a very quick background, very brief background on large eddy simulation. This is really textbook material. Then I will move on to LES-ROM, so build a LES-ROM framework, explain why we should do that and how we do this. And then in part 3, this is more technical, and I will talk about how data can actually improve LES-ROM. In particular, I will talk about data-driven LES-ROMs with a focus on variation multi-scale. This is related to what Samuele presented before, and quite a few others are working on. I'll end up with some conclusions. At any point in the talk, please stop me. Again, I would like to get as many questions as possible and get your feedback, either online or offline. Okay, this is the group of people that has been working on these problems. These are my former students and postdocs. Birgül is going to join Tomas's group. Chahong is going to Wisconsin. So previous students and postdocs. And these are my collaborators. I left aside some of them, and I apologize for that. I just wanted to focus on the material presented in the talk. The last group, Paul, Tamai, and Jeffrey. So these were my collaborators a decade ago. We worked on LES for geophysical flows, and that's what I'm going to be talking next. So the motivation, in order to illustrate LES, I decided to go with an application that we studied, and this is the thermohaline circulation. So this is illustrated here, the movement of cold and warm masses of water in the ocean. And this is joint work with Tamai, Paul, and Jeffrey. We decided that this is, we started to think about these large-scale phenomena, and we decided that with the tools we have, we just cannot tackle those. So then we said, okay, let's look at a smaller scale phenomenon, and this is the Red Sea overflow. So what happens in the Red Sea, the overflow in the Red Sea, and this is a small scale by geophysical standards, small scale phenomenon, but the length scales are on the order of kilometers, okay? Okay, so to do so, we realized very quickly that to tackle realistic parameters, we cannot use a brute force approach, DNS, the direct numerical simulation. So the tool that we used was large Eddy simulation. This is one slide, crash course on LES, and I apologize for that, but yeah. So the idea in LES is very simple. Many of you know this. You've written books on this. So the idea is that, so here you have a signal, the orange signal, the maroon signal, yeah, that has both large scale components and small scale components. The small scale components are the oscillating components, right? The point is that you'd like to approximate this signal on a coarse mesh. So this is your numerical mesh. That's what you can use. How do you do it? And the idea is very simple. The idea in LES is that instead of representing all the components, you try to represent only the large scale components. And this in orange would be U bar. So this is the filtered, spatially filtered signal flow variable that can be indeed represented on the coarse mesh. Of course, you lose all the small scale information, okay? Okay, so to do so, you need a couple of ingredients. You need a spatial filter, denoted by G delta in here, and you can have this either in the physical space, Gaussian filter, for example, or the Fourier space, like the sharp cutoff. The next step is to filter your variable. Yeah? So you apply the filter, that is a convolution, but it doesn't have to be, and you get the large scales. U bar is the filter flow variable that represents the large scales. Of course, you need equations, and you get those by filtering the original underlying equations, Navier-Stokes in our case, and then you solve these filtered equations for the filter variables. Easy peasy, right? So this is one slide for LES. How do you do this in practice? So if you look at the Navier-Stokes equations written right here, you realize right away that you have the closure problem. You have a nonlinearity, and that's when filtering, gives you an additional term that you need to model. This is the closure term. There are different ways of doing this. I'm not gonna get into this. It's physical, functional, or structural, mathematical, and we're gonna use those in the round setting as well. Just want to share the numerical results. So this is the dam break problem, also known as the lock exchange problem. You study mixing. You have cold water and warm water separated. You release the wall between them, and you let them mix. This would be at the lower Reynolds number what happens if you use a fine mesh. If you use a coarse mesh, that's what you get. I'm gonna go back and forth to show you what the difference is. So one difference is that the mesh here is much finer than the mesh here. I mean, I hope that this is clear. But you can also notice that the small scale features that you encounter in this fine resolution simulation will not be seen in the coarse resolution simulation under resolve regime. What you're gonna see is some average features, and that's okay. If you use LES, that's okay. And this is the paper we published in Ocean Modeling in 2009, so more than a decade ago. I'm really old, okay? So this is, I think, the best illustration of what LES does. So we calibrated our results for a small Reynolds number, 30,000. Okay, that's the curve, the solid curve. Then we used a bunch of LES models to predict what happens at the high Reynolds number, 1 million. By doing so on a coarse mesh in an under-resolved regime, we decreased the computational cost by orders of magnitude. So it was really an achievement, a computational achievement. The take-home message is not about the actual application, but the take-home message is that in realistic flows, you have to deal with under-resolved simulations. And this was emphasized by Samuele in his talk as well. Yeah? And here I'm writing implies LES. You can use other techniques, but you have to do something. Here's a controversial slide. So this is one of the this is state of the art in LES. This is Pierre Sagat's book. It is an atlas of LES models. There are hundreds of models, not thousands of models. I want to emphasize there is also mathematical support for it. Here I'm advertising. I'm biased. I'm advertising our book. Thomas is gonna say that, okay, so here, so his book with Roger should be used instead. whatever you use, I just want to emphasize that this is textbook material. LES is a settled field, more or less. Yeah. Okay, now, why do I talk about this? I think that the important thing is to realize what happens in the reduced order modeling community. So in this slide, I present the standard Galerkin ROM. You've seen this. You start with the PDE, very general form. You expand in terms of your POD modes, let's say, could be anything else. You project in a Galerkin projection. R, the dimension is very small, and you get your Galerkin ROM. Reduced order model, lower dimensional dynamical system. Yeah, think of R as order 10, 100, yeah, not 1 million. For Navier-Stokes, this is the equation you get. A dot is equal to matrix A times A plus A transpose tensor B times A. It's very simple. It's low dimensional, very simple. Does it work? And this is a slide that is what I call the elephant in the room. I think the answer is it depends. If you start with the 2D flow past the cylinder, this one in the left, the top left corner, then the answer is yes. If, however, you go to the quasi-geostrophic equations or to the turbulent channel flow, the answer probably is no. And here's why. So here you can see that in red, we have the 2D flow past the cylinder, the decay of the singular values of the eigenvalues, right? Squares. Yeah. Look how fast they decay. That's why this problem is something that everyone likes, including myself, right? ROMs work for this problem. But if you go to the QGE, quasi-geostrophic equations, a chaotic system, or to the turbulent channel flow in green, look how slowly they decay. You would need a lot of modes to actually make the ROM work for you, which is okay, but this is just the turbulent channel flow. In engineering applications, you're gonna need hundreds or even thousands of modes. What do you do then? Okay, so I think that the point I want to emphasize is that we have, like, just like in standard CFD, we have an under-resolved regime that is relevant in realistic applications. Samuel also talked about this. Yeah, I'm saying here you should use LES ROM, but Gianluigi might say RADS ROM. So it depends on your taste, but you should do something. You should do something. Okay, so what do you do? And in this slide, I just repeat the LES type of approach. That's what we're using. So we choose a spatial filter, could be projection. Samuel talked about this. I'll talk. It's very popular in the ROM community, but it could be something else, like the differential filter. I'll mention this as well. You filter your variables to get the large scales. You get the filtered equations, and you solve the filtered equations. At the end, you get an LES ROM, which is the standard Galerkin ROM supplemented with a closure term. To me, in a nutshell, that's what closure is. Okay, there are different ways of doing that. Yeah, I have to rush to this, but I mean, so the closure models in the ROM community are different flavors. So, some in the audience recognize their names, some should recognize their names too. There's functional, that's probably the most popular. This, think, energy dissipation type of models, eddy viscosity, for example. Yeah? Or structural, this would be mathematical, more mathematical, mathematical arguments. But there's a third type. This is data-driven modeling. This is a survey paper that Omer's son is putting together with his students and his collaborator in Norway, as well as Bernd Nowak. So we're trying to give an overview of what happens if you want to do data-driven closure modeling, for example. Yeah. So there are different types of approaches. I'm not gonna talk too much about all of them because I don't have time, but I want to give you the main idea. So as in classical LES, the most popular, I believe, the most popular way of doing closure modeling in reduced order modeling, ROM, is to use this the statistical theory of turbulence. Okay. Now, in a Fourier setting, this is very clear. It's been settled, a long time ago. You have here a couple of schematics of, so like the energy spectra for different Reynolds numbers. So for various Reynolds numbers, you have the energy dissipation going from large scales to small scales, experimentally, numerically. Everything is pretty clear. Okay. Natural question is, how about ROM? And the study that I like very much by Couplé, Sargon, Badevant, JFM 2003, shows that for backward facing step, you pretty much have the same picture. So energy is dissipated from low index POD modes to large index POD modes. Okay, that's a non-homogeneous flow. It's not Fourier based. It's just a POD, classical, regular POD. So there is hope. However, this is a potentially contentious slide. I want to say that stability, energy dissipation stability is not enough. You need accuracy. And stability does not imply accuracy. It's necessary, but not sufficient. Okay. And I say this because I got a question a long time ago. How about you use a Galerkin method? Isn't this stable? It is stable. We proved this for finite elements. We proved this for Galerkin methods, incompressible flows here. Yeah, we proved that. But as you can see, you can add either too much or too little stabilization, and you don't get the accuracy that you need. Nevertheless, let me start with, in the last 5 minutes or so, let me start with what we've done first, and these are eddy viscosity models based on this idea of energy dissipation, energy cascade. This is a 3D flow past the cylinder. Reynolds number was 1000, not very high. Flow comes from the left. You can see that displays structures, yeah, 3D, yeah, structures. And what we did was very simple. We compared different LES type of techniques. POD is Galerkin run, 6 modes. All of them use 6 modes. ML is mixing length. So this is a very simple model that Lumley came up with, decades ago. You can see that if you don't do anything, you have too much energy in the system. Look at the red curve. If you use mixing length, but you don't choose the parameters the right way, you can see that you dissipate too much. So too little dissipation, too much dissipation, right? Then we try to look at more fancier LES models like Smagorinsky, like the variational multiscale related to what Samuele talked about. Angelo, Michel also did pioneering work on the VMS models, Gianluigi as well. Yeah? And the dynamic subgrid model. This is state of the art in LES. We said, okay, let's try it. Yeah, we're the first to look at this dynamic model. Yeah, and you can see that if you use improved, more complex LES models, you get closer to the actual results, DNS results, FOM results. Okay, so what I want to say is that pretty much we got the same type of conclusions as in classical CFD. Yeah. So if you use standard type of models, you don't match the energy spectrum. If you use more complex LES models, VMS, dynamical subgrid scale, you get better results. Okay. All right. Now I need to hurry up a little bit. So the second type is structural. No eddy viscosity whatsoever. This is based on ideas coming from image processing, proximal deconvolution. To my knowledge, we're the only ones to use proximal deconvolution closure models. Yeah. This time we have a spatial filter with a length scale delta. Okay? And we go through the usual LES run framework, look at our closure model. So the closure model has an approximate deconvolution of the filter variables. Not only this, but the differential filter is self-adjoint. We move the bar to the test functions. We have a few test functions, we filter them, and then we store them. That's a nice trick. This way you don't have to compute the filter variable at each time, they're online. Okay, so this is just a second type. Now, the last one I want to talk about in the last couple of minutes is the data-driven model. And this is something that Gianluigi and his group is also looking at. There are other people as well. It's based on VMS idea, Tom Hughes, simple and general. It's a very good idea, I believe. And this is based on decomposing the scales into resolved and unresolved scales in a Galerkin or Petrov-Galerkin procedure. Yeah, very simple. You can do the 3-scale decomposition. We've done that as well. So yeah, it's general framework. It's a general framework. And this is our algorithm. So basically, we look at our closure term. This is right here. And this is from the data, FOM data, full order model data. And then we try to fit through the data our ansatz, which is a matrix A tilde and the tensor B tilde. So offline, we fit these closure operators through the available form data. Simple idea. Then online, we just use the matrix A tilde and the tensor B tilde to correct our Galerkin ROM, so as closure models. Does it work? It does work. The 2D works as well. If you push the 2D flow past the cylinder, Reynolds equals 1000, so it actually breaks down, and the 3-scale model gives better results than the 2-scale model. What helps us is actually physical constraints, and I want to emphasize these are important. Yeah. So basically, what we do, we have imposed physical constraints on the closure operators, A tilde and B tilde. We impose those based on what happens at the Galerkin ROM level. Okay. They do help. Again, 2D flow past the circular cylinder in the predictive regime, the physical constraints do help. Finally, let me just say a couple of words about the quasi-geostrophic equations, a significantly more difficult test problem, displaying gyres. We tried this test problem from Greatbatch and Nadiga. So 2D gyre forcing term, the Galerkin ROM does not reproduce the correct pattern for gyre pattern in the time average. Whereas the data-driven model does it, and if you add corrections, you get an improvement in the accuracy. Okay, the Galerkin ROM does not work. Right. Finally, this is Chang Hong's, my student. He's just defended his work on 3D turbulent channel flow Reynolds tau 395. Corresponds to 13,750 on the bulk velocity. Not very high, right? Very difficult for the ROMs. Very difficult. Everything we know pretty much doesn't work, okay? All right, so I'm gonna show you second order statistics. It turns out that what works for us is a hybrid approach. We use the data-driven structural modeling, and then we add just enough dissipation and the viscosity. Yeah? It turns out that this hybrid approach in practical, well, for turbulent channel flow computations works best, okay? This is mirroring what happens for classical LES, so we're very excited about this. We have to look more into finding the optimal model, but it seems that the hybrid models are a good approach. Okay, finally, I just want to say that we're trying to prove things. We're mathematicians at the end of the day. This is one of the results on verifiability of closure models. The idea is very simple. If you can guarantee that the closure model is good in some sense, can you also say that the LES ROM solution is close to some average right here? We can prove that, and we illustrate it numerically that this theorem as well. Okay, so these are my conclusions. Oh, I'm sorry. So for realistic flows, I hope I made my case that we would pretty much work in the under-resolved regime. LES ROM is a good approach. If working classical CFD should work here. Data, I believe, is important. And actually, if you use an LES ROM approach, I think that you can prove things. I think that's important as well. Okay, these are the, I would be happy to talk with you more about this if you have any questions, papers for eddy viscosity, proximal deconvolution, and what we like most nowadays, data-driven models. Thank you, and I will stop my presentation here. Sorry, thank you.
Okay, thank you very much, Traian, for this motivating and clarifying talk, okay? It's really, really motivating. Thank you. Okay, are there any questions?
I have maybe a quick question. When you take you talked about filtering the basis function. So are you filtering the ROM basis functions there? Do you need to filter all the ROM basis functions, or do you get to choose which ones?
Okay, so let's see, Ian. So Ian is my student. He's just starting. This is an excellent question. So when I say, I think that this was about the approximate deconvolution ROM. When I said filter basis functions, I meant filter all the basis functions. Now, if you have 1 million basis functions, that's gonna be an issue. And this is why finite element people don't do that. But if you only have, handful of modes, or even, a few dozens, this is something that you can do offline once, store them, and then use them online as many times as you want. So to answer your question, I filter all the basis functions, but the run space is relatively small, so I can afford to do that. Whereas FOM people, full order model people, can never do that.
Okay, thank you.
You're welcome. That's a good question.
Okay. More questions? Hi, Sam.
Yeah, Traian, thank you. That's a really interesting talk. Could you just comment on this in the data-driven approach? You said once you split the whole problems into 2 scales or 3 scales.
Correct.
I mean, what's the difference and why did you do that?
Okay, that's a good question. I had some discussion. So in the VMS community, so this is Tomas and Samuel, so they know more about this. But in the classical finite element community, there is a discussion about 2 scales, 3 scales, whatever scales is worthy of investigation or not. In our mind, I think that the idea of this is Tom Hughes' idea, by the way. Yeah. So the idea is that for us is that it allows you more flexibility to do modeling at different levels. You see, so you have the large scales that you resolve, and then you have the unresolved scales. Okay. Now, in statistical theory of turbulence, there's this idea of locality of energy transfers. So the idea is that, right, so you would like to model things that are neighbors in terms of scales. Now, it's also conceivable that you might want to do something between unresolved and large resolved scales, and maybe do something else between large resolved scales and small resolved scales. So you could, in principle, use different models at the closure models at the 2 separation ranges. It's flexibility, right? It's flexibility. Worst case scenario is that you use the same model everywhere. Okay, so it's a 2-scale model, but it's conceivable that you might find different closure operators, and that's what happens to us for the different ranges.
I see.
Right. So it's not my idea. It's the variation multi-scale idea. It's a general framework, and it's very flexible. You really can think about modeling the different scales. I think that's what's nice about Hughes' idea.
Okay. Thank you.
Okay, thank you.
Good question.
Any other question? Okay. Well, I just wanted to know in the estimation of your additional terms A tilde and B tilde, I think these were for the convective and diffusive parts of the operator. Is it?
Right. Right.
So you follow a data-driven approach by minimization. Okay. So my question is how rigid is that functional to minimize?
Excellent question, Tomas. So this is not rigid at all. I mean, people ask this question all the time, and this is a very natural, very good question. Why A tilde and B tilde? The only reason is that that's what you have in the Galerkin ROM. In fact, you can think about cubic terms and higher order terms, so it's just simply different models. But whatever you do, you should come up with something, instead of A tilde and B tilde, a general function, but that function has to be easy to evaluate in the online stage. As long as you do that, any type of modeling is appropriate. So the answer to your question is it was convenient because it matches the Galerkin operators, but other functions can be, and I think should be, we're thinking about this, investigated. That's a very good question.
Okay, thank you.